This PhysCast involves an application of Gauss's law for electric fields. Pause the video and read the question carefully. Let's begin our solution with an interpret step. In this problem we have a plane horizontal distribution of charge that is uniform, and we're told what the surface charge density is. We want to know what kind of particle, in particular what mass of particle, with a particular charge can be held suspended above this distribution of charge. So this is going to involve an understanding of the field from a charge distribution, in this case a plane charge distribution. Further, the question is going to involve understanding the electric force balancing the weight force. That's what we really mean by levitation here. Moving on to our develop stage, draw a diagram here. Here might be our horizontal surface, and we're told it has a uniform negative charge distribution on it, and we're told what that surface charge density is. In this case it's minus 0.8 microcoulombs per square meter, and we're interested in a charged particle here with minus 5 microcoulombs on it being suspended some distance above that surface. The two forces of interest here are the weight force, which we know is just going to be mg if we're near the surface of the Earth, and the electric force on that particle, which we can think of as the charge of the particle multiplied by the electric field from that charge distribution. Importantly, for a plane distribution of charge, Gauss's law tells us that that simply depends upon that surface charge density sigma and 2 times the permittivity constant. And that comes about, which you should check in your lecture notes or textbook, by the consideration of a Gaussian surface, a small cylindrical Gaussian surface that basically penetrates through as indicated on the diagram there. If you consider the field lines through the various parts of this surface and apply Gauss's law, the result you wind up with is as indicated here. Some important values we get from this question are the size of the charge, which in this case is minus 5 microcoulombs. We also need to perhaps look up and remind ourselves the gravitational acceleration constant here, 9.8 meters per second squared. We'll also need the permittivity constant, which in SI units is 8.85 times 10 to the minus 12, and the units for that are coulomb squared per Newton meter squared. Now we're ready to do our evaluation step. In our evaluation step, we simply want the weight of this particle to be equal to the electric force from this particle, which will be the charge multiplied by the electric field, which Gauss's law tells us in this case will be given by that, and we can rearrange this equation to find the mass that we're looking for. Will be Q sigma divided by 2 epsilon 0 times G, and these are all values that we have. I'll simply do it in terms of magnitudes in this case. We've already taken into account the vector nature of the forces in the problem, so we can simply write this in terms of magnitudes. There's our 5 microcoulombs for our charge, multiplied by our surface charge density, 0.8 times 10 to the minus 6 in coulombs per square meter, divided by 2 times the permittivity, 8.85 by 10 to the minus 12, multiplied by the acceleration due to gravity. And when we do that calculation, we wind up with a number here of 23 by 10 to the minus 3 kilograms, or we might prefer to write that as 23 grams. Importantly, in this problem we had two heights that we were asked about, whether this was 1 centimeter or 1 meter above the surface, but Gauss's law showed us that the electric field from this plane distribution of charge is independent of distance from the sheet, and importantly that was only true if we considered distances small compared to the size of this sheet of charge. We essentially were considering the sheet of charge to be infinite in extent. Now, we weren't told in the question how large this horizontal plane surface was, so we're going to assume for the time being that at both 1 centimeter and 1 metre height above the surface, we're still a long way from the edges of the sheet, which will be extending off some large distance. So in fact this is the mass for both of those distances, for both A and B, as given in the question. Now we should finish with an assess step. One nice thing to do in our assess step here is to make sure we haven't made any mistakes in our rearrangement of formulae, to make sure we get the right units. So we have here, if we look at our expression here, we have charge in coulombs multiplied by surface charge density, which was in coulombs per square metre, and that's divided by 2 was just a number. Our permittivity here has units of coulomb squared per Newton metre squared multiplied by G, which is in metres per second squared. A little bit complicated here. This coulomb times coulomb cancels with this one on the bottom. This per metre squared cancels with this per metre squared on the bottom. So what I end up with here is, if you rearrange that, a Newton per metre per second squared. And all I need to do now is remember that a Newton is a kilogram metre per second squared divided by metre per second squared, and my metres and seconds squared cancels out nicely, and I'm simply left with kilograms, which is what I needed for a mass. So my units seem to check out, my rearrangement of the formula seems consistent.